Hi everyone, I wanted to take a few minutes and walk through the Math 85 pre-test with you in case there were some questions that were a little bit unfamiliar. The first question asks you to simplify the expression 3x squared y all raised to the power of 3. What this requires is the removal of brackets. There's nothing that we can do inside the brackets with the 3x squared y, but we have to take that expression 3x squared y, and when it's raised to the power of 3, that power applies itself to everything inside the brackets. And there are a few pieces in here that you have to be extra careful with. So that power of 3 is going to apply itself to the 3 out front, or that coefficient of 3. So essentially you'll have 3 to the power of 3. You're also going to take x squared and raise it to an additional power of 3. So when you see power of a power, you want to multiply those powers together. So 2 times 3 gives us x now to the power of 6. Now that power of 3 also applies to that sneaky little y. Y is currently being raised to the power of 1. So once again, 1 times 3 gives us an overall power of 3. Now, if you can evaluate numbers that are on the small side, I prefer you do that when you're simplifying. So 3 to the power of 3 does not mean 3 times 3. It really means 3 times 3 times 3 again. So we know 3 times 3 is 9. 9 times 3 one more time is 27. So our final answer is 27, x to the power of 6, y to the power of 3. So that should be answer D on your multiple choice. The next question has the same set of instructions. It's asking you to simplify 3, and then we see a bracket with x squared minus 2x inside those brackets. Then we have minus 4 bracket x plus 1. So let's talk a little bit about what we see here. If you're following a proper order of operations, or what we call the BEDMAS rules, then we want to work inside the brackets first. But if I take a peek at x squared minus 2x, there's nothing that can be put together. They're not like terms to be combined. Same thing's happening with the x plus 1. We can't work with the x plus 1 quite yet. So brackets are taken care of. There are no exponents to apply powers for. But now we have to take care of division or multiplication in terms of those orders. So we have a 3 out front of a bracket, and what that means is we're going to take that 3 and multiply it through every single term inside those brackets. So when you have 3 times x squared, we know the result is 3x squared. 3 times a negative 2 is going to give us a negative 6 as our coefficient. And again, we've got an x as our variable in that term as well. Now we do the same thing with minus 4 or negative 4. We want to distribute that through the second set of brackets. So negative 4 times x is going to be a minus 4x, or negative 4x. Negative 4 times a positive 1 is going to be negative 4. Now we seem to be finished, but there are some like terms that we need to collect or put together. So negative 6x and negative 4x are like terms. They have exactly the same variables in them. So we can put them together by adding or subtracting those coefficients. 3x squared stays as 3x squared. But negative 6 minus 4 more puts us further into the negatives. So negative 6 minus 4 is going to give us negative 10 of those x's. And then we have a constant term of minus 4 still at the end. So not only did we open up those brackets, but we collected like terms in order to simplify that expression. So the correct answer for question number 2 is option A. We have yet another simplified problem in question number 3, but this time it looks a little bit different. We have 2 bracket x plus 1, which really means we're going to multiply 2 by x plus 1. And then we have another touching bracket. So because those 2 brackets are side by side with nothing in between them, we know we need to multiply those as well. We have a couple of options here. What we can do is distribute the 2 through that first set of brackets only, and then that 2 has been absorbed. We would then multiply that result by 3x minus 2. That's not my favorite way to do problems like this. If you ever have something where you need to distribute a number out front, but you also have 2 binomials, so these are 2 two-term polynomials that you have to multiply together, this is often what we call a FOIL problem, where you're going to multiply first terms, outer terms, inner terms, and last terms. So I like to FOIL or multiply those two binomials first, and then I'll distribute that 2 after the fact. So let me show you what that looks like. If we leave 2 and we multiply that by x plus 1 and 3x minus 2 as binomials, I'm going to leave that 2 out front for now and worry about multiplying x plus 1 and 3x minus 2. So the F in FOIL stands for first. What that means is we want to multiply the first two terms in these brackets. So x times 3x is going to be 3, but x times x gives us an x squared. So there's your new first term. O is for outside or outer. And the outer term means we're going to multiply x by negative 2. So x times negative 2 is negative 2x. Whoops, we've turned on the eraser here. Let's just fix that. X times negative 2 is negative 2x. Now we have I for inner. Inner means we're going to multiply these two inside terms. So 1 times 3x is a positive 3x or plus 3x. And L is for last. So the last thing we're going to multiply are the last two terms in each bracket. So 1 times negative 2 is going to give us a negative 2 at the end. So we have now multiplied the binomials together. We still need to take care of a little bit of cleanup here. So if we look inside those brackets, we see like terms again with our two middle terms. 3x squared stays as 3x squared, but negative 2x plus 3x's, again, combine your coefficients. Negative 2 plus 3 is a positive 1. So you have plus 1x or plus x. Both of those mean the same thing because we have an imaginary little 1, sneaky little coefficient of 1 up front. So we also have that minus 2 as the constant at the very end. So now we're ready to multiply or distribute that 2 through everything inside those brackets. So we're going to have 2 times 3x squared to give us 6x squareds. 2 times x is going to be a positive 2x. And 2 times negative 2, your constant, is going to be negative 4 or minus 4. If you take a look at your multiple choice options, that aligns with option D. Example number 4 is another simplified problem, but the difference here is that all of a sudden we're introducing or reintroducing negative exponents. Negative exponents require some sort of finagling or some rearrangement. We know, and I'll just do this on the margin of our page here, we know that if you have something like x to the power of negative a, so some abstract power, it can be rewritten with a positive exponent if we pack it up and move it across essentially the division line. So if we pack that up and move it into the denominator of a fraction, that power moves from negative to positive. So this is the same as putting that x to the power of positive a in the denominator. But this looks a little bit funky, so we want to make sure that it looks like a proper fraction, and we put a 1 as our placeholder. Now, if it were in the denominator of a fraction already, so let's say we had something like 5 all divided by x to the power of negative a this way. Again, if you have a negative power, you want to pack it up and move it over that line in order to make it positive. So if I can imagine packing up x to the power of negative a and moving it across that division line, it's now going to be part of the numerator. So 5 is happy. 5 is okay in the numerator position. X to the power of now positive a is going to join it. So we're going to use those rules when we simplify this expression. So when I take a peek at what we see here, the only thing in bad position or bad form is that x to the power of negative 3. So I'm just going to highlight it. That's the only piece that we need to pack up and move across that division line. So when we do that, sometimes what I like to do is rewrite everything that's in perfect position as it is. So 2 is happy in the numerator because it doesn't have a negative power attached to it. 7 and x are perfectly happy in the denominator because they don't have any negative powers associated with them. But x to the power of negative 3 is going to move downstairs to become positive. So when we do that, it becomes x to the power of positive 3 in the denominator. So to clean this up in one more step, we have 2 in the numerator and 7 as your coefficient in the denominator. But x times x to the power of 3, don't forget there's a sneaky little 1 here. When you multiply bases that are the same, you need to add your powers. So x to the power of 1 plus 3 gives us a total power of 4. So our final answer is 2, all divided by 7x to the power of 4. Question 5 comes with a different set of instructions. You are asked to factor the following expressions. So if we see x squared plus 3 times x minus 28, we factored in prerequisite courses. If you took Math 75 on campus, it would be Module 2, where you factored all kinds of different expressions. When you factor something, essentially you break it down into its multiples. So x squared plus 3x minus 28 is some simplified expression. We want to factor it and break it into two components where we would multiply those two components to get, as a result, your original expression. Whenever you see a trinomial, we're calling this a trinomial because it has 3 terms in it. You want to remember that trinomial factoring is often going to be the reverse of sort of the FOIL process. So what we need to do is decompose this. We need to figure out what two binomials are going to multiply to give us x squared plus 3x minus 28. There are a whole bunch of different ways you might have been taught this factoring technique. What I'm going to do is largely encourage you to use trial and error. There are modules coming up in Math 85 where factoring is an essential skill, and you have to know how to factor quickly and efficiently as you go. So when I see an expression like this, I start with the x squared and I ask myself, what two terms in those first positions will I multiply to get x squared? So in this case, it has to be x times x. Now, I actually skip the middle just for a moment and I think about factors of negative 28. So these last positions need to multiply to give me a negative. So what I know for sure is that there is 1 plus and 1 minus, because when we multiply a positive by a negative, we get a negative result. Now think about factors of 28. Factors of 28 could be 1 and 28, because we know 1 times 28 gives us 28. We have 2 and 14. 2 times 14 gives us 28. Or we have 4 times 7 to give us 28. Now, because this is a simple trinomial and there is no coefficient, the two factors that we choose must multiply to give us negative 28, but they have to sum together to give us the middle term of positive 3x. So let's say I put 4 and 7 in positions here. I'm just going to check to see if this is right. I'm going to show you a check that I often use in class to help students factor quickly in their minds. I'm going to show you something called the SMILES check. If we were to draw a baby smile, 4 times x is positive 4x. Now draw a big smile. X times negative 7 is negative 7x. If you were to combine those two middle terms, 4 minus 7 is negative 3x. We have the right number, but it's the wrong sign. That middle term needs to be a plus 3x. So essentially we have the right numbers, but we don't have them associated with the right symbols or signs. So that's not the correct factoring for x squared plus 3x minus 28. If we were to switch those signs, so let's try this again. We've got x times x to give us the x squared, and then 4 times 7 gives us 28. But let's switch those signs. You have a minus 4 and a plus 7. So if I do that little SMILES check really quickly, negative 4 times x is a negative 4x. and x times positive 7 is a positive 7x. When we add those together, negative 4 plus 7 is in fact positive 3x. So I know we've factored that correctly this time. So this little smiles check works really well when you have simple trinomials or when you have general trinomials, because sometimes there's a coefficient in front of that x squared that kind of throws off the middle term. So this factoring technique might make practicing these kinds of skills a little bit easier. So the answer that is correct for question number 5 is x minus 4 times x plus 7, or option C. Just as an aside, if you wrote this as x plus 7 times x minus 4, that is also correct because of the commutative property of multiplication. If I said 7 times 4 or 4 times 7, order doesn't matter, we get the same answer. We have another new set of instructions for question 6. We're asking you to solve the following equation. We're asking you to solve the equation for x, which means we want to know what x equals. So when you hear that word solve, it means tell us what that variable is equivalent to. So the equation we have is 3 with a bracket, and then we've got x plus 1 equals 2x minus 4. So the first thing we need to do is identify the type of equation this is. This is what we call a linear equation. It's just an x to the power of 1, but we happen to have x's on both sides of the equation. So we also have a set of brackets that we need to clean up or contend with. So let's distribute that 3 first. 3 times x gives us 3x, and 3 times positive 1 is, of course, plus 3. That's equal now to 2x minus 4. If you're solving a linear equation, you want to get your x's to one side and all of your constants to the opposite side. You can do this in as many or as few steps as you're comfortable with, but I'll do this in smaller stages here for you today. So if I want the x's all together, I'm going to push that 2x to the opposite side. In order to do that, I need to apply the opposite operation. Because we're essentially adding a 2x, we must subtract it from both sides to balance the equation and move it. So essentially we get 3x minus 2x. We still have that plus 3 hanging around, but when you move that 2x across the equal sign, it disappears. So you can think about subtracting 2x from both sides. We still have negative 4 on the right side of your equation. So now we can do a little bit of cleanup and collect these as like terms. 3x minus 2x is a single x, or just x. If you rewrite this as plus 3 equals negative 4, then you just have one more step to contend with. And again, you might have skipped this altogether and gone straight to your final answer. So if we want to pack up and move that plus 3 over the equal sign, again, we have to apply the opposite operation. We want to subtract 3 from both sides in order to make that happen. So you'll have x equals negative 4, now minus 3. So think about your integers. Negative 4 minus 3 more puts us further into the negatives. Negative 4 minus 3 is a total of negative 7. So our solution to this equation is now x equals negative 7. Once again, in question 7, we're asking you to solve, so we need to figure out what x equals. This time, though, the equation is a degree 2 equation. We have x squared minus 5 times x plus 6, and that is set equal to 0. In order to solve this equation, because it's not linear, it's not just a single x, we can't just push the x's to one side and the numbers to the opposite side. That strategy won't work. It's not legal math. What we need to do instead is break down this degree 2 equation to factors. So x squared minus 5x plus 6 is a trinomial, or a 3-term polynomial, that we can break down as 2 binomials. So once again, this is the reverse of your foiling technique. I look at x squared as my first term, and I ask myself what 2 terms are going to multiply to give me x squared. So in this case, it's x times x. Skip the middle for a second and take a look at positive 6. Factors of 6 are either going to be 6 and 1 or 2 and 3. Now, both combinations, 6 and 1 can be combined to give me a 5. 2 and 3 can also combine to give me a 5, but the signs are going to tell us which one is actually correct. Whatever I multiply in those last two positions, my result needs to be a positive 6. So in order to get a positive as my result, I need either two negatives or two positives. And because that middle term is a negative, it's telling us that both signs must be negative. So if I think about factors of 6 and both of them being negative, -2 and -3 will multiply to give me positive 6. But if I do my little smiles check here, -2 times x is -2x, and x times -3 is -3x. When I combine those middle terms, we get a -5x, which is exactly what we're looking for. So now that we've factored the equation, we haven't actually solved anything yet. If we know that x minus 2 or x minus 3 could be equal to 0, we use something called the zero factor property. What that tells us is maybe x minus 2 on its own is 0. So we have to solve that little mini equation. It also tells us that maybe x minus 3 on its own is equivalent to 0. So if I know the equation x minus 2 is set equal to 0, and I ask you to solve it for x or to get x by itself, I'm going to add 2 to both sides. So if you add 2 to the left and you add 2 to keep your equation balanced on the right, 0 plus 2 is going to be positive 2. If we do the same thing for x minus 3 and we get x all by itself, we have to move that -3 over to the right side, so we're going to add 3 to both sides. So 0 plus 3 is going to be positive 3. What that means is we actually have two solutions for this equation. We have x equals 2 or x equals 3. So your final answer should be D for question number 7. Now in question number 8, we are asking you to find the slope or the steepness of a line that is defined by the equation 2x minus 5y equals 7. This is something we call the standard equation of a linear function, or the standard equation of a line. It's just written in a very specific way. If you ever want to look at the slope of a line, you need to put it in what we call slope-intercept form. So if I jot down what slope y-intercept or slope-intercept form looks like, that equation needs to be written in the form y equals mx plus b. So what that means is y is all by itself. Then on the right side of the equation, you have a coefficient in front of the x, or the x term, and then you have a constant term of b. If your equation looks like this, m is the slope or steepness of a line. Remember, that's rise over run. And b is the location of the y-intercept. So if we can rearrange this equation so that y is isolated and we match this format, we'll have slope-intercept form. So the first thing I want to do is push that 2x over to the right side. So we'll get -5y. If we move that 2x over, it's positive on the left, so we need to subtract it from both sides to move it. We'll have -2x, and that 7 remains positive, so we'll have +7. Now, true slope-intercept form has y all by itself, so what we need to do is get rid of that coefficient for y. This means we have -5 being multiplied by y, so to undo multiplication, you have to do the opposite, which means we're going to divide by -5. But we can't just divide the left side by -5. You have to divide everything by -5. So you can do that as individual terms, or you can do that as a complete side. So now we have y on the left. A -2 divided by a -5 results as a positive 2 over 5. Then we've got that variable x. A positive 7 divided by a -5 is overall -7/5. So what that tells me is the location of our slope can be found as the coefficient of x. So we know that the slope, or m, of this linear function is 2 over 5. So for every 2 we rise, we run horizontally 5 units. If you're counting from one point to the next, on this linear function. So m equals 2/5 or A is your final answer. Now let's take a look at question number 9. It says the y-intercept of the equation y equals negative 4x plus 2 is, and then it's giving us some coordinates to choose from. There are two different ways I'm going to show you how to find the y-intercept. Because this format already looks like y equals mx plus b, we know negative 4 is the slope, and we know 2 is the location of the y-intercept. So we know that this graph crosses the y-axis at positive 2, but we have to be careful about the coordinate. When you're imagining a y-intercept at positive 2, you're crossing the y-axis here. I'm just sketching it for you at 2, so we're not even going to put a scale here. So one of my coordinates is going to pass through the graph at 0, positive 2. So the coordinate we're looking for here is 0, 2. So that would be answer A. I want to show you a second way to find the y-intercept, and this works no matter what type of equation you are given. So what we know about every single y-intercept in the whole wide world is that if we let x equal 0, we know we're crossing that y-axis. So if I take that original function, y equals negative 4x plus 2, and I take that x out and I replace it with a 0, we'll get negative 4 times 0 plus 2. And of course, 0 times anything is always going to give us 0. 0 plus 2 is positive 2. So we know the location of the y-intercept, again, is at positive 2. Because it's a y-intercept, we know x is automatically 0, and our y value was calculated as positive 2. So you've got two different ways to find the y-intercept. The second method works really well when you have nonlinear equations. Last but not least, we're asking to solve an inequality. So there's no equal sign. There is just a less than sign. So we're solving 3x minus 6 is less than 4x plus 8. I want you to sort of treat this inequality kind of like an equal sign. So we're going to balance things by moving them across that less than sign. But you have to be a little bit careful with some of our steps later on in the process. So I like to read inequalities with the variable or the letter on the left side and the number on the right side. So we want to push that 4x over to the left-hand side. So in order to do that, we're going to subtract it from both sides. So you'll have 3x minus 4x, still minus 6 is less than 8. So combine those like terms, 3x minus 4x is a negative 1x or negative x. You still have minus 6, and that is less than 8. So from here, we want to push that minus 6 over to the right. So you have negative 1x is less than 8, but when minus 6 joins the right side, you have to add it or do the opposite operation. So we're going to add 6 to both sides. So what that gives us so far as a result is negative 1x or negative x is less than 8 plus 6 or 14. Now we want x all by itself, not negative x. So what we need to do is divide by negative 1. But there's something very special or unique that happens anytime you divide or multiply an inequality by a negative. You need to flip that sign. So instead of x being less than negative 14, that less than sign needs to change its orientation and it becomes greater than. 14 divided by negative 1 is negative 14. So the proper answer for question number 10 is option C. So again, the takeaway from here is that when you divide or multiply, so we're going to write this out, when you divide or multiply an inequality by a negative, you must flip the sign. So that's one of those rules that we hope sticks in the back of your mind when we have to work with inequalities a little bit later in the course. If you have any questions about this pretest or want to go over other examples, please make sure you let me know as soon as you can.